Hi, today I want to talk with you about page performance. And I think this is an important topic for us to be discussing because it affects all of us. It doesn't matter what framework you use, what vertical you're in, who your customer is. Everybody benefits from and appreciates page speed. Moreover, I think it's fair to say that as an industry, we have not been delivering good performance overall. At the end of last year, a mobile website on average was taking 14 seconds to load over 4G. And when the connection dropped to 3G, that number goes up to a whopping 19 seconds. These statistics and other performance metrics ultimately matter because they can be thought of as a proxy for the user experience. A slow page not only frustrates users, but it's going to change their behavior as well. When your page is slow, the user's going to close that tab, or they're going to switch to another tab, or they might even just subconsciously start using your application less. This has been shown in a couple different case studies. So if we want to build products that users actually engage with, it's important for them to be performant. More than anything else, my goal for tonight's presentation is for you to walk away with a framework for thinking about performance. When I first got interested in performance, I was really excited to apply what I was reading about to the work I do at Fitbit and see if I could improve our performance. But I was really surprised when I went to go apply certain techniques and I found that they didn't have an impact. And when I couldn't come up with a good explanation for this, and the internet didn't seem to have a very good explanation, or at least explicit explanation either, I felt like I needed a better framework and way of thinking about performance so I could focus my efforts on techniques that were actually going to make an impact. One of the first things I realized is that performance is highly variable and it's context specific. You can't say that your page loads in 2 seconds without qualifying that by saying what device it's on or the network it's on. However, if you're looking at the performance for a particular page, you can roughly approximate the variables that you're dealing with as the network, the browser, and the hardware. These are going to interact with your app to result in the performance that your user experiences. The interesting thing to note about the app is we have full control over it. We may shoot ourselves in the foot in how we design and build it, but that's up to us. We get to make the decisions about how it's designed and built. On the other hand, the 3 things I just mentioned, the hardware, the network, and the browser, are all things we cannot control. We cannot control if a user is experiencing poor network connectivity. We can't control if they're using IE8. We can't control if they're on an old phone. In other words, these are basically all constraints that we have to work with. So in a way, I realized that when we talk about performance, what we're really doing is trying to change what we can control, which is the app, to better accommodate the constraints introduced by things we can't control, which is, in this case, the network, the browser, and hardware. When I mentioned earlier that I was finding some performance techniques that weren't having an effect on the performance in the app I was working on, I realized it was because those techniques were designed to address a constraint that didn't exist in my particular system. What you see up on the screen is the mental framework that I came to help me address the performance issues I was seeing. And this is going to be the framework for the rest of my discussion tonight. I'm going to talk about how the network, hardware, and the browser all constrain performance, and then how you can identify these constraints and techniques for mitigating them. So let's get started. How does the network affect performance? When we talk about the network, there's a tendency to talk about it in terms of bandwidth. You'll always hear telecom providers talking about their upload or their download speeds, but you'll never hear them talk about, say, latency. That's interesting because with the exception of some applications like video streaming, most applications are not constrained by bandwidth. The graph I have up on the screen shows the results from a study where they were interested in understanding how bandwidth affects page load. However, after about 5 megs, increasing bandwidth didn't improve page load at all. And to put that in context, the average American home user has 40 megs of download. And over mobile, that's about 20 megs. And so the idea that increases in bandwidth speeds in the near future are going to alleviate the page speed issues that we're experiencing is not accurate. On the other hand, latency is a constraint. Does affect performance. And what is latency? Latency is the delay that arises from information having to travel between 2 locations. In the United States, if you wanted to send information round trip between the 2 coasts, you can expect that to take between about 60 and 70 milliseconds. And unlike bandwidth, latency has been shown to strongly correlate with page performance. In the same study again, they this time varied latency, and it was shown to have a strong linear relationship with the page load time. Unfortunately for us, it's pretty expensive to improve latency. It requires spending a lot of money and ripping up cables and putting new ones in the ground or replacing copper connections with fiber optic connections. For example, in the slides I have up there, that was used for high-frequency trading. They spent $300 million to shave 6 milliseconds of latency off, which shows you how much money is in high-frequency trading. Unfortunately, that's not all of it. We also need to take into consideration the concept of last-mile latency. And last-mile latency refers to the fact that typically the worst latency you experience is not on those long jumps or sending information over long distances, but rather getting the information between the user and the edge of the network, basically getting the information to the internet backbone. You can kind of think of the internet backbone architecture kind of like a system of roads. Once you get to the interstate, you can make really good time, and you don't have to switch roads very often. You can just fly. But getting to the interstate takes you some time, especially if you're have a 4-way stop signs and a lot of stoplights. And last mile latency is kind of like that. Once you're on the big internet backbones, information can travel very quickly, but getting there takes a lot of time. And last mile latency is almost even more cost prohibitive to improve because there's less users on those local links, which makes it harder to make the cost justification for updating those connections. In just a second, I'll talk about how you can identify the effects of network constraints in your app. Before I do that, I wanted to introduce the 2 performance tools I'll be talking about today. One needs no introduction, and that's Chrome DevTools. The other is Web Page Test. So webpagetest.org is an open source tool. You can download it and run it on your own, or you can use the online version, and it allows you to easily test performance across different devices or different locations and different internet speeds. And I like it because it's really easy to get a nice sandbox environment. You need to remember that when you're benchmarking performance, your internet connection matters, whether or not you have different extensions running in your browser matters, how many tabs you have open matters. So using a separate tool in a separate environment makes it really easy to make sure you're getting accurate and consistent results. After you use Web Page Test, it will spit out a bunch of charts and diagnostic tools that you can use to identify performance issues. And a lot of these charts or similar things can be also found in Chrome DevTools. However, I'll tend to favor the Web Page Test charts today because they're a little bit easier to screenshot. So, understanding latency in your app. If you want to understand how latency is affecting your app, you want to start by looking at the waterfall chart. Each row in the waterfall chart represents a different resource that is loaded by your application. And the colored bars denote different parts of the download process. To understand latency, you want to be looking for the lighter colored segment of those bars. The lighter colored segments of the bars represent time to first byte, which is exactly what it sounds like. It's the amount of time after a request is made before the first byte is returned. And time to first byte can be is partially influenced by latency as well as how long it takes your server to return a response. So if you're consistently seeing high latency, that means it could be a constraint or it could be indicating that you have some issues going on with your server. On the other hand, for bandwidth, you're going to be looking for the content downloaded bars, which are indicated in the darker shade. And for these resources, increasing bandwidth would improve performance. We're talking about 3 specific tactics for accommodating network constraints, and that is using a CDN, minimizing requests, and using HTTP2. CDNs, or content delivery network, are going to improve performance by moving your content closer to users and therefore reducing the effects of latency. However, it's not a complete solution because it can't alleviate last mile latency, which, as I said, is part of the biggest problems facing in terms of performance. If you're unsure of whether you're using a CDN, you can use web page test to determine this. It will flag resources that it does not detect as using a CDN. And this is under the Performance Review tab in web page test. Next, minimize requests. It's important to minimize requests even if you still end up sending the same amount of data, just wrapped up into one connection versus multiple connections, because there are non-trivial costs associated with establishing a new connection. One round trip to the server is going to be required to set up the TCP connection, and then if you're using TLS, additional 2 round trips are required. And increasing bandwidth is going to have no effect on this. Those costs are determined entirely by latency. If that wasn't enough, because we're using TCP, it's affected by TCP slow start, which means that the connection does not send data at the maximum rate initially. It kind of warms up to avoid overloading the network. One of the things I found interesting about this is you can start to logic about what the trade-off is between sending more data versus more requests. I always wondered whether I should be sending less data, but maybe split into 2 requests because I'm being really exact, versus just sending everything in one big request. And depending on if you know the latency of your system, you can calculate this. If it's not using TLS, so there's going to be that 1 round trip required for setup, and so the latency of your system is approximately the cost there, versus if you're using HTTPS, that jumps up to 3 times latency. The average website loads over 100 requests, though I've found it fascinating to realize that New York Times makes 441 requests, which leaves a significant room for improvements in terms of minimizing requests. I'm not going to talk about concatenating files because I think that's kind of obvious, but I did want to mention with HTTP cache headers, both web page tests and DevTools make it pretty easy to check to make sure that you're using these correctly. Caching is not going to improve performance on initial page load, but it will improve performance on subsequent page loads. Pretty obvious. Don't load resources you don't need. And I like to use DevTools to poke around to see if I'm loading resources that are not necessary. But while I'm doing that, even though the whole gist of this presentation so far has been that latency is the constraint, see if your images are fully optimized. About half of the requests that are made by a website are for images, and about 75% of the data loaded on a website are images. So there's a lot of low-hanging fruit there to reduce the weight of your website by checking to see if you can pare down images. And 2 things to look for is whether you're loading images at a larger size than you're actually using them, or whether they can be compressed better. And 2 tools I like for that are TinyPNG and TinyJPEG. And lastly, but perhaps most importantly, minimize redirects. There's a tendency on an initial page load to redirect, because maybe the user's trying to access HTTP, and you want to send them to HTTPS. Or maybe you want to direct them to a different subdomain. However, this redirect is going to delay everything that comes after it, because the page load can't begin until after that initial redirect has finished. When you're looking for redirects, you want to look for a 300 level code. If the redirect is server side, it should have a 300 level status code. And the last technique I want to talk about for accommodating latency is HTTP2. They should have named it something different. HTTP2 was introduced in 2015 with the goal of using the network more efficiently efficiently and reducing the perception of latency. And that truly was its focus. In fact, if there was any criticism around the protocol, it was that it was very narrow in scope. It just really was designed to address some of the concerns around latency. In terms of performance, the biggest change introduced by HTTP2 is multiplexing, which allows the same connection to be used to fulfill multiple requests at the same time. And having just talked about the setup costs for a new connection, it's easy to see why multiplexing would be a big performance improvement. Multiplexing, by enabling multiple requests to use the same connection, cuts down on the amount of setup costs you have to go through for a new connection. About 75% of, about 3/4 of users right now can use HTTP2. Most browsers introduced support for it in 2015. However, both with IE and Safari, it only works for certain operating system versions. By website, about 12% of the internet uses that. I wasn't able to find any statistics on what percentage of traffic handles it, but I wouldn't be surprised if it's a little bit higher because a lot of the high traffic websites currently use it. In some ways, you could think about it as a simple change. It's a server-side change you enable on the server, and then if the browser supports it and you support it, the browser will automatically switch over to using it. However, in reality, your implementation of HTTP2 will probably entail a little bit more than that, and will be a little more nuanced. Realistically, you're going to have to enable TLS, as is not required by the web specs, but most browsers require HTTP2 to be used in conjunction with TLS. In addition, you have the choice of whether you want to undo the optimizations you made to accommodate for HTTP1. And two examples of such optimizations would be concatenating all your files to minimize requests, or image sprites, which combine multiple images into one image to, again, minimize requests. And then monitoring performance. You probably should be doing this anyway, but it's a good idea to understand whether this actually improved performance. And on that note, the effects that you might see from HTTP will probably vary. It depends partially on the latency that you're currently experiencing in your system. If latency is a big constraint for your app, you're going to see more improvements by switching over to HTTP2 than someone else that's maybe more bandwidth constrained. It depends on whether you're using TLS already. If you're already using TLS, HTTP2 will probably be a performance improvement, but if you're not, TLS does introduce 2 additional handshakes in that connection setup, and so the performance improvements brought around by HTTP2 might kind of cancel out the addition of TLS. And then lastly, you have some choices as to how you want to address HTTP1 optimizations. Most interestingly is whether you want to stop concatenating files. And there's a really interesting write-up done, I think it was by Khan Academy, talking about their experiences with HTTP2. They implemented it, they're really excited to see performance improve, and it didn't. And so they started digging into why that was happening, and it turns out it wasn't the protocol's fault necessarily, it was the fact that they were no longer concatenating files. And what was happening was that current compression approaches work better on a larger corpus. And so when you're compressing one large file, the compression algorithm works really well and is able to spit out a much smaller file. But when you use that same compression algorithm across a bunch of smaller files, it offers very little improvement. So long story short, there's a lot of nuance in applying HTTP2. Next up, I want to talk about how browsers impact performance. The browser's load and the page load process is substantial. It's responsible for taking the markup you give it and generating it all the way into the pixels that you see on the screen. However, the browser's way of doing things can become a bottleneck if it gets stuck waiting for external resources to load or for JavaScript to execute. And this is not inherently bad. This prevents us from experiencing what you see on the screen, which is what's called a flash of unstyled content. However, we want to avoid doing it unnecessarily. So how do we identify unnecessary render blocking? First, you need to be aware of when page render is occurring. And there are two things you can look for in web page test. One is you can look for when web page test reports that page render has started. And it does this by taking screenshots and seeing if the page is all white anymore. Or you can look at when the browser thinks it started painting. And sometimes there's a discrepancy between these. I usually tend to go by when a web page test thinks it started painting, because that's ultimately what the user sees. The user doesn't care when the browser thinks it started painting. It cares when they actually see stuff on the screen. So those are the two things to look for. And so, one, external resources. Look for when the page starts rendering, and then ask yourself what resources are required for this to happen. And then, is there a way that these resources can be delivered more quickly? Here, everything on the page, not just the stuff for page render, could be delivered more quickly if that initial redirect was eliminated. Another common anti-pattern to look for here is CSS or JavaScript triggering the load of resources, or in other words, resources that aren't discoverable to the look-ahead parser. And then JavaScript execution. Web page test highlights JavaScript execution in pink. And not all JavaScript execution is bad. That JavaScript that's executing might be vital for delivering content onto the screen. But sometimes there are analytic scripts running maybe before the page is loaded. And if so, you should delay those later to give the browser the resources to focus on other things. And that's another thing. Sometimes, even if JavaScript is executing before page render, and it's not necessary for page render, removing that JavaScript or shortening it might not improve performance. It depends on whether that JavaScript is blocking something else that's more important from occurring. I'll be talking about two techniques for minimizing render blocking. To deal with JavaScript, we'll be talking about the defer tag, and to deal with network requests, we'll be talking about inlining. Deferring scripts is a good technique for scripts that are necessary for your overall page, but not for the initial render. One of the biggest sources of bloat on page is having a million tracking scripts. And while you're probably required to have those, they're not necessary for page render, and you can defer them until once the page is loaded. You commonly hear defer mentioned along with async, and so to clarify the difference between the two, both of them do not block the parser. The difference is that an async script will execute as soon as it is loaded, whereas a deferred script will not be executed until after the document has been parsed. So a deferred script will always execute at the same time or later than an async script. Inlining is when you put CSS or JavaScript in your initial HTTP response instead of loading them as separate resources. And like the other tactics we've talked about today, there's nuance in how it's applied. When it's done well, it can improve performance because there's less waiting for network requests. When improperly applied, it can impair the look-ahead parser, or it can decrease load times on subsequent page loads, or increase page load times on subsequent page loads because resources are not being cached. Luckily, it's been pretty clearly established how to capture the benefits of inlining without the downsides. And that is to deliver your critical content in under 14 kilobytes and then load your remaining resources asynchronously. The reason why it's important to deliver that content in under 14 kilobytes is that the first response from the server can only contain 10 TCP packets, and that's due to TCP slow start. And 10 TCP packets can hold about 14 kilobytes of data. And so if you keep your content under 14 kilobytes, the browser can start to render things as soon as the response returns. And then for loading remaining resources asynchronously, for JavaScript that's pretty obvious, but for CSS that's sometimes less obvious. And the Filament group put together a tool that makes it easy to do that, and that's called Load CSS. And lastly, let's talk about how hardware impacts performance. But I'm going to take a drink first. We've all been told that we should make sure to test our code on devices besides our laptops. But what is it that's different about these devices that makes it important to test on them as opposed to just making our browser window smaller? When we're talking about performance, it usually comes down to the fact that different devices can carry out computing processes faster than others. And thus, hardware or processing power bounds computationally intensive tasks. And computationally intensive tasks within the page load process are typically either expensive JavaScript. So that JavaScript might be expensive because there's just a lot of it. So for instance, loading a framework on your page. Or it might be expensive because it has poor complexity. And then expensive rendering, a good example of this would be if you have animations. And that's when you sometimes notice the jank and the stutter, particularly on mobile devices. As developers, it can be easy to take for granted all that's going on under the hood when we execute JavaScript. There is a lot going on, but to talk about it on a high level, basically the browser's JavaScript engine in Chrome, that's V8, and Firefox, that's SpiderMonkey, is taking the JavaScript, parsing it, it has to compile it, and then it's executed. And I think it's useful to talk about that process on a high level, because when we do, it's easy to abstract out what the inputs are that affect the performance costs of JavaScript. The parse and compile phases are going to be affected by how much code you're giving it, whereas the execution phase, the costs associated with that are going to be affected by the performance of your code. These costs then become more or less apparent depending on the device that you're running on. Rendering also has performance costs, and the process there is a little bit different. The browser has to parse the document to generate your DOM and the CSS object model. Those are then combined into the render tree. The calculations are done to figure out layout, and then paint is done. And there are a lot of different variables there that determine how costly that operation is overall. One is the number of elements affected, selector complexity, layout complexity, paint complexity. By paint complexity, I mean painting a gradient would be more expensive than a solid color. And for the sake of time today, I'm not going to go in depth on improving CSS performance. Mostly, I just want you to be more aware of the fact that styling can have performance costs. When looking for CPU-constrained processes, you're going to want to focus on what's going on in the main thread, which in the waterfall charts and web page tests are the very bottom bar. Well, second to bottom bar. And for expensive JavaScript, you're looking for large blocks of yellow. These indicate long-running JavaScripts. And ask yourself, what are these blocking? Some scripts, if you improve their performance, they'll speed up performance. But other scripts, if you speed them up, they're not blocking anything. It doesn't matter. And the effects of these of CPU-constrained processes are going to become more apparent depending on what type of device you're running. So this is the exact same website loaded on desktop and mobile, and you'll see that same script on desktop takes about 0.4 of a second to execute, whereas on mobile that jumps to a second. That'd be a real bad phone. And expensive rendering, same thing, only this time you're going to be looking at the main thread to see and looking for long blocks of purple, which indicates layout, or large blocks of green, which indicates paint. In this example, this is from the W3C specs, and seeing that much time spent in layout is really suspicious regardless of the page, but in this case, I mean, the page looks like it's from 1998. That's super suspicious. And so when you look at your waterfall chart, you notice there's a JavaScript file that's clearly kicking off something to do with layout. And when you pull up that individual file, you see that it is altering the DOM, and that causes layout to have to be recalculated for the entire page. And it's a page with hundreds of nodes. So how do we fix this? There's going to be 3 things that I talk about here. One is loading less code. Another is replacing unperformant code or styling. And lastly, reducing the responsibilities of JavaScript. Removing unused code. You can go loading less code. There's a couple ways you can go about doing this. One is a very obvious, remove unused code. Do some spring cleaning on your libraries. Another is loading less code. So a problem a lot of applications face is that you're loading more code on a page than what you need for that particular page. You're perhaps loading all the code for the entire app instead of what you just need at that moment. And so Webpack, in conjunction with code splitting and tree shaking, can be used to adjust this. I'm just going to talk about this at a high level because Webpack could be its own week-long seminar. Code splitting is nice because it allows you to generate more granular code bundles, which allows you to more closely match up the code that you're sending down with what the front end actually needs. And then tree shaking is a technique for, making sure that you're only sending down code that's necessary. Tree shaking works by making sure that only code that you need is included in your final bundle. And that's the opposite of dead code elimination. And lastly, be careful with frameworks and libraries. They have a performance cost, and across the board, if you used a vanilla JavaScript, they're going to load a lot faster. The example I have up on the board is for a simple to-do MVC app. So that app is probably multiple magnitudes more simple than whatever you work on. And you'll notice vanilla JavaScript takes 50 milliseconds. Ember takes an incredible 2 seconds to start up. And that's a to-do MVC app. Replace unperformant code or styling. If you notice in web page tests that there's a expensive render or scripting process and you want to investigate it more, this is a good time to go to DevTools and do some profiling. What I have up on the screen is what that profiling currently looks like. However, starting in Chrome 58, so Chrome 58 is Canary right now, Chrome 56 is the current release, this is going to change. The timeline page that I just showed is going to turn into the performance tab. So keep an eye out for that. That's changing. And then lastly, reduce JavaScript's responsibilities. Sometimes we use JavaScript for tasks that could be handled by something else. So sometimes we can use less JavaScript by using perhaps HTML and CSS instead, or perhaps unloading some of that work onto the server. So with server-side rendering, you kind of have to decide what you're optimizing for. To speak in broad generalities, server-side rendering is going to deliver you a faster paint. But the trade-off there is there's going to be a longer window between when the page is painted and when it's interactive. And that can be a little weird to users. So you kind of have to decide which is more important. However, server-side rendering is going to have less variation in performance, and that's because your server is doing more of the work, and you can control the server, and your server is a constant, versus your users' browsers and devices carrying out the work, and there's a wide variation in devices. And it does better for SEO. That's all I have. If there were any things I wanted you to take away from this presentation, I highly encourage you to go home and try out web page test, and then just ask yourself, is it the hardware, is it the network, or the browser that's constraining the performance that you're seeing in your app? Thank you.